All right, take out your highlighter. We're going to highlight this piecewise notation. We sometimes can't describe a function all in one equation. And the absolute value function is an example where you can describe it in two pieces. So for example, when you have oh, there we go. It's just a little bit of a delay. When you have an absolute value of a function, we've learned that you could graph the inside first and then flip whatever's below above the x-axis. So when you're graphing the absolute value of x, well, y equals x is this line that would continue, and when we flip the dotted part up and over, we would get this line. What it ends up doing is gives you an equation for two different graphs put together. One part is, oops, I'll do it in blue. This part here, we could describe as just the line y equals x. The green line is the line of y equals negative x. And so when we want to describe the absolute value graph, we can either write it just as the absolute value of x, or we can describe it as two different pieces. One piece is when y is equal to x, but that's only when x is bigger than or equal to 0. And the other piece, which is the green part, y is equal to negative x, that only happens when x is less than 0. Basically what happens is in order to reflect the negative part up over the x-axis, we multiply the whole equation by a negative 1. So we can highlight this here as it explains. To write an absolute value in piecewise function, start by identifying where it's positive and where it's 0 and where it's negative. So let's say you have y equals the absolute value of x plus 2. If I graphed x plus 2 would have a y-intercept of 2 and a slope of 1. It would look like this. That would be the graph of y equals x plus 2. Wherever the original inside graph is negative, that part gets reflected up. So when we try to write the piecewise function for this, we say that it's equal to x plus 2. That was the original inside when it was positive. In other words, when the x values were bigger than or equal to negative 2. And we take the part that got flipped up, and you can write it like this, or you can take the original and just put a negative in front of it. Because flipping it over the x-axis means you can take the original equation and multiply it by a negative 1. And so the part that gets flipped is when x is less than negative 2. So when we go here to example 3, they want us to write each function in piecewise notation. So some of the things we're going to need to find, the critical point. Which is the x-intercept. We can do this by graphing the original function. So if I take 2x minus 1 So I'll call it the inside function. If we graph y equals 2x plus 1, we know that that is a straight line, has a y-intercept of 1 and a slope of 2. If I graph that off to the side here, y-intercept at 1, a slope of 2 means you would go up 2 over 1. This is our critical point right there. Where do we have an x-intercept? How do you find an x-intercept? Algebraically, make y equal to 0. So one way that you could do it, if you can't see it easily from the graph, you can make y equal to 0, move the 1 over, divide by 2, and we can find that critical point at negative 1/2 comma 0. Just a review from yesterday. Yesterday we practiced graphing absolute values. So if I wanted to graph the absolute value of 2x plus 1, it would look very similar to the graph above. You would have this critical point at negative 1/2 comma 0. There's a negative sign. This section of your graph, the black section of your graph there, would stay the same. But this part that's negative, which I'll highlight here in green, it will get flipped up. So when we want to write this as a piecewise function, we can say that the absolute value of 2x plus 1 is equal to, it's equal to 2x plus 1 when it was positive. Nothing changed. When did that happen? When x is bigger than or equal to negative 1/2. That black section of the graph is the same on both the absolute value and the inside function. But the green section of the graph gets flipped up. And we can show, or I'll write it in green even, we can show it being flipped up by just putting a negative in front. That negative has the effect of changing all your y values from negative to positive. That's what flips it up. And this is the piecewise notation for this graph. It's describing each part separately. Yes? Was the original question 2x minus 1? And I did 2x plus 1 the whole way through? Okay, so just wait for it. Oh yeah. Yeah, there we go. We just changed the original question. Put a plus sign. That's better than changing every single graph that we had all the way through. Right. Just change the question. Right. If you change the question on an exam like I just did here, I would lose a 1/2 mark. Well, if I was a student doing this, okay? Because the mistake that I made, only 1/2 mark, because the mistake that was made did not make the question any easier, okay? If you had a question that said, solve for x, and it was really hard for you, and you said, I would rather solve this one, x plus 1 equals 3, and then you would lose more than just because you solved a completely different question.
Well, you just changed one sign and pretend like you didn't see it.
Well, in this case, that's what I did, right? I just changed the sign. It's like a stupid, silly mistake. You would lose a 1/2 mark for that.
You got like one freebie.
No freebies. Wouldn't that be nice?
There might be a bonus question worth like 100.
All right. Part 2, Part B. Again, we want to find the critical points. We want to graph the inside function first to see what this graph looks like. How would I find if I have negative x squared minus 3x? How would you graph that? What strategies would you use from your parabolas unit to graph this? None?
Oh, parabolas.
Okay.
I was still doing y.
Could you find the x-intercepts of this? What would you do? If you were finding the x-intercepts, could factor out a negative x, leaving you with x plus 3. X-intercepts at x equals 3 and x equals negative 3. And so we can plot those. Where's your vertex going to be? At negative 1.5 comma something. Which way is this parabola going? Down. So I know that my vertex is somewhere here. I don't know exactly where it is, and I'm okay with that right now. I have an x-intercept here at negative 3, 0, another x-intercept here at 0, 0. This is the graph of negative x squared minus 3x, not clearly labeled because I don't have my vertex labeled. Okay? But it's not asking us in this question to label the vertex. What is it asking us to do? It's asking it to write it in piecewise. Okay? So if this is the graph of y equals negative x squared minus 3x, then what happens with an absolute value? You would still have these critical points at 0 and negative 3. This part of the graph, which is the y values are positive, would stay the same. But the part of the graph that's below the x-axis, where the y values are negative, draw it in black, they would get flipped up. Right? These parts here, where my y values are negative, they get flipped up, and this would become the equation of negative x squared minus 3x. So when we go to write this in piecewise notation, we have that the absolute value of negative x squared minus 3x is equal to. Let's look at this first black piece. It got flipped up. So we can take our original equation and multiply it by a negative. You could simplify that if you wanted to make it x squared plus 3x, or you could leave it like that. When does it get flipped up? When x is less than negative 3. The green part didn't get flipped. That was part of the original graph. That graph stayed the same. When did it stay the same? Between negative 3 and 0. And then it got flipped up again when x was bigger than 0. Piecewise notation just says take the graph that got broken up and write it in different pieces. In this case, we had two parts get flipped up, so we could end up writing everything in 3 pieces in total. Sometimes you'll see piece 1 and piece 3 combined when they just say x is less than -3 or x is bigger than 0, and put those together because there's the same thing happens to both of those pieces. Okay, questions to try. 8, 9, and 13.